Hey guys, today we're going to prove a theory that Galileo proposed. When a pendulum swings, whatever the mass of the ball that you're using as the pendulums, or whatever the amplitude you do, so if you do it from like here, or from here when you swing the pendulum, it doesn't matter, it will always be the same time. And as I said, we're going to prove that theory. But what does matter is the length. I'm going to tell you a formula that we can use to calculate how much time it will take to do 10 revolutions. So I go 1, 2, 3, like that, 10 times. We'll figure out how much time that would be, and then we'll actually try it, and it's going to be that time. Here we go. Physicists always use the unit meters, so that's what we're going to use because that's going to work for the formula. But I figured out a meter is 39.3 inches approximately, but then we have to do something. The length will affect the radius of this because the string is going to be at the middle of it and to the side then going up. So the length of the string has to be a meter minus the radius of the ball, which is 1.5 inches. 39.3 minus 1.5 is approximately 37.8. So that is the length of the string that we will need to cut. The pendulum is hung. Let's start doing our calculations and then proving Galileo's theory. So you can see the pendulum behind me. First, I'm going to tell you the equation that we have to do to figure out the time for 10 revolutions. First, we're going to figure out 1 revolution though. So that equation is the time equals 2 pi times the square root of g over length. G is 9.80. It's a gravitational acceleration. It's 9.80 meters per second per second. It's meters per second because every second it goes 9.80 meters per second faster when you drop something. So once again, the equation is time equals 2 pi times the square root of g over L length, which is 1 meter in this case. Okay, and then you multiply by that by 10 to get 10 revolutions. For this part, I need a little helper to help me. Come on up, helper. There we go, the helper. Come on, ready to help me? Yes. Let's start. We're going to start figuring out the time. We're going to use the calculator. Okay, so 2 pi, we'll type 2 pi. There you go. It says 2 pi. Then we're going to say 2 pi times, 2 pi times the square root of g, 9.8. Okay, then we're going to say divided, that's just like a fraction, divided by the length, which is 1 meter in this case. There we go. See it? Okay. Now we'll say equals, we get 19.66948124. We're just going to round it to the nearest tenth, which is 19.6. As you know, my reaction time to stop the time is it's not accurate. So I don't know, about 0.1 or 2 seconds is my reaction time. And then our length isn't perfect. This length may not be exactly 1 meter, okay? It may not be 1 meter. It may just be a little wrong, okay? But remember, 19.66 is the magical time in this case. What's your checklist? Pendulum, check. Timer, check. And helper who's gonna swing the ball let's start. Let's get this to clock. We're in calculator still. Clock. Here we are in clock. My brother's right there holding the ball. And when I say go, he's going to leave it. We are going to actually count the oscillations with him. Okay, so just a test run. Can you drop it? Done, 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 done. So if it goes back and forth, that's 1. Okay, so there we go. You got it? Yep. Okay, now let's start proving Galileo. Dun, okay, clock will go to stopwatch. Okay, so it should be about 19.6, okay? So when I say go, leave it. The time is here. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 19.77! We have it! We proved Galileo! And we are correct. Yep. So that equation does work. Galileo was right. Now, as I said, the length varies. But if you put it from there or here and you drop it, it doesn't matter the time. But I also said the mass doesn't matter. Let's prove the mass statement. Let's go. It's hard to choose the heavier ball than that orange ball to change it to prove mass. Because you need the same radius or the length will vary and then you'll get a different time. So we're going to use a baseball that has a radius similar to the orange, but just a little bigger, but it's okay. So we're going to use this baseball. We're going to need to use more tape too because this is heavier. So, see you later when this becomes a baseball. We have the baseball on the pendulum. We have to use way more tape. So it should still be 19.66 the time. It's because the length is the only thing that makes the time vary. But this time we didn't change the length. We changed the mass, which should be the same. So we're going to prove Galileo in a second way in this video. My helper's holding the ball again, right there. And then, you want to do a test run again? Yeah. Sure? Drop it. 1. Yeah, that's good. Got it? Okay, good. The helper's good. And now, let's do the time. 19.66. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 19.38, we proved Galileo! Yeah, woo! So, there we go. Galileo proved it a second time. I hope you had fun watching us prove Galileo. And now you know about these principles of physics. And thanks for watching. Thanks for watching.